is really short and quick. It's the one-to-one property, which you did problems like this in Algebra 2. You maybe didn't call it the one-to-one property. Okay. Then we're going to, after we finish this problem, we're going to look at graphs of exponential functions. So we're going to be graphing things. And then after graphs, we're going to look at compound interest, which are two formulas you should be familiar with already. Okay, so we've got kind of three topics we're going to discuss. All right, here's our one-to-one property. A to the x equals a to the y if and only if x equals y. This should make sense to you if you just think about that. Note that in the one-to-one property, it is important that the two bases for your exponents are the same. So it's like base A for both, right? So like think about that in terms of numbers. 8 squared will only equal 8 squared. So if I put any other exponent in, it's going to equal some other number, right? So if you have the same base, then the exponents have to be the same for it to be equal. Now, look at the problem that I gave you. Can you use one-to-one as is right now? No, because they don't have the same base. But in some cases, you might see that you could rewrite one or both of the bases so that they would have the same base. Now, you have to be really thoughtful here. Okay. When you rewrite, you don't want to change what the number is. So you don't want to like put an exponent in that would make it some other value than it is. You're just rewriting it in an exponential form, but it's still equal to the same thing. So this is like the hardest part of the one-to-one property. Okay, do you know a connection between 2 and 8? 2 cubed is equal to which value? 8. So which one of them are we going to rewrite? The 8. We're going to rewrite 8 so that it has a base of 2. And if we rewrite it as 2 cubed, it's the same thing. So we're not changing the equation, we're just changing what it looks like. Okay, so let's do that. 2 to the 2x minus 5 equals 2 cubed to the x minus 3. Hello. Thank you. Oh, she's not here. Probably golf or something like that. Thanks. Okay, so this is really important. A lot of times people make the mistake of putting a cube over here because they want to say 2 cubed is 8. But then if you're cubing the left side, by the golden rule of algebra, I should also cube the right side, right? But this is not cubing this side, it's just rewriting it. Okay, by power of a power property, what do you do with these two exponents? Multiply, so you'll have to distribute the 3. That's 2 to the 2x minus 5 equals 2 to the 3x minus 9. Is this now set up so that I could use one-to-one property? Yeah. It looks like a to the x equals a to the y. So I'll write that off to the side. So they're the same base now. And that's only true if x equals y. So I can say 2x minus 5 equals 3x minus 9. And of course, this is a very simple equation for you to solve. Get x's on one side, numbers on the other. I believe it's x equals 4. Now, if you ever want to check your answer to see if your answer is correct, the one thing I will caution you is make sure that you take your answer, x equals 4, and you plug it back into the original problem. Don't plug it into the one that like you changed bases to, because if you miswrite that, if you change the wrong base or you make it not actually the same equation, then you will have solved a different equation and it'll still work. Okay, but we want to plug it back into this one up at the top. So that would be 2 to the 8 minus 5 when I put in 4, and 8 to the 4 minus 3 is 2 cubed equal to 8 to the first? Sure. Okay. So you do have that option to plug it back in and make sure that it's a valid answer. Any questions on one-to-one property? Okay, always be thoughtful. Don't always just jump the gun. Just double check. I rewrote something, but I didn't change what it was. It's still equal to the same value. 2 cubed is still 8. Okay, now we're going to get into the graphing section. So, what is an exponential function? The most basic form is going to look something like this, a to the x. If you have your Algebra 2 notebook and you look at it for like to compare to what we're doing now, we probably wrote it as b to the x because b was for base. But our textbook uses a, so I'm going to do that as well. And then there's a couple of things to note about a. A has to be greater than 0, so that means no negative bases. And then a cannot equal 1. How do you recognize when something's exponential and you should be thinking about the things that we're going to see here in a moment? Well, the variable is up in the exponent. So instead of the polynomials like x to the 5th, x to the 4th, x cubed, now it's 5 to the x, 2 to the x, 1/2 to the x. Okay, you have a number base, and then you raise it to a variable exponent. Okay, so I'm going to show you 2 graphs down below. I don't think you need to necessarily write these down into your notes just because it's a lot, but I will post these notes online, so if you want to come back and look at these and investigate them further for yourself, you can. But I'm going to start with f of x equals 2 to the x. Okay, so that's exponential because the variable is in the exponent. The base is 2. I made a table of values, and this you probably did last year in Algebra 2. So I just chose some different x values. When I don't know what a graph looks like, I always try to choose some positive, some negative, 0, that kind of thing. And then back in Algebra 2, I always choose some numbers that are far out, like 100 and negative 100, just to prove a point. Okay. So do you agree when you raise anything to the 0, it's equal to 1? And then 2, the first would be 2, 2 squared would be 4, and we could keep going, right? And are you okay with the 2 negatives there? A negative exponent doesn't make things negative, it flips what it touches. So 2 to the negative 1 becomes 1 over 2 to the first, and 2 to the negative 2 becomes 1 over 2 squared, or 1/4. Now, would you all agree that like without a calculator, if I asked you to do 2 to the 100, you don't know the answer? But at the very least, you could agree that that number is very large. Okay, so I just said it's a big number. It's way out there, right? Okay. And then, likewise, if I put in negative 100, that would flip it, and it would make it 1 over 2 to the 100, which would be 1 over a very large number. And 1 over a very large number is really close to 0. So this was a point that I would always do in Algebra 2 to prove that as we go more and more negative for our x's in this particular graph, we're going to get closer and closer to 0, but theoretically, will we ever get there? No. So this was probably the first time you were introduced to the asymptote, right? You had a horizontal asymptote at y equals 0. And then a lot of times I know like geography maybe studies populations, and they call these curves J-curves. So if that helps you to think about the shape of an exponential function as like a J, you could call it a J-curve. Now I did another graph on the other side, okay, and the other graph that I did, notice I changed it, it's 2 to the negative x, and then, you know, what we just reviewed about negative exponents, they don't make things negative, they flip things, so that's really 1/2 to the x. And then I put in some of those same numbers, and I got some values. But do you see it's kind of like a reflection in the y-axis? To have the 1/2 to the x instead of 2 to the x. Okay. So there's a difference in your J-curve, or your graph, based on the value of your base. So in this one, the base is greater than 1. Originally, this one looks like the base is greater than 1, but there's a negative, so we know that that would really flip it. The base is actually 1/2. So, of course, the base is greater than 0, but it's less than 1.
So if the exponent is negative, do you want us to like do all our work in the form where it's positive?
You could do either way. I prefer the positive exponent because then I'm less likely to make a sign error when I put in a negative and make it negative, you know? So you can do whichever one. You should get the same answers. So I'd be okay either way. But I like changing it because I can see that b is between 0 and 1. B is not actually greater than 1 right there. Do you remember the 2 words that you would use for these different types of functions?
Growth and decay.
Yes, exponential growth when b is greater than 1, and exponential decay when b is between 0 and 1. So if you want to add that into your notes, there's 2 versions of an exponential function. There's a growth function and there's a decay function. You might want to add that down, like when it's growth, when it's decay. If you want to draw like a quick sketch of what a graph would look like, you could do that too in your notes, just so you know. Now, one other thing before I leave this one that I just want to talk about is like why we call them exponential growth and decay. So when we refer to exponential growth, sometimes people, like looking at these 2 graphs, they mistakenly think that it has to do with increasing and decreasing, and that's false. If I were to reflect this blue graph for y equals 2 to the x over the x-axis, do you agree it would look something like this?
Yep.
Okay, and we could say, like, let's call this g of x. If I reflect it in the x-axis, what did I do to the equation? Put a negative out front. So this is negative 2 to the x. And, like, this is good for us to review. That base isn't negative. The base is still positive 2. The x is only touching the 2. But the function was made negative, so everything that we put in gets made the opposite. Okay. But that graph is also exponential growth. And so this graph is decreasing as you go to the right. So just to kind of review, what does exponential growth and decay mean? Treat it like stair steps for like slopes. Obviously, we don't have constant slope. It's not a line. But what's happening to my stair steps? They're getting bigger and bigger. And that's whether I'm going increasing or decreasing, right? So when we talk about exponential growth, we're saying the rate of change is increasing faster and faster and faster. I also like sometimes make a note to myself, if you want to jot this down in your notebook, when it's growth, you're moving away from the asymptote. You take off or you drop suddenly and you move away from the asymptote. If it's exponential decay, you move towards the asymptote. So like if you're looking at your rate of change, your slope, the steps are getting smaller and smaller until it looks like they're not really changing at all. So we're saying the rate of change is decreasing. We call this one g of x equals negative 1/2 to the x. But those are both decay functions. So just a little side note, I know that sometimes come up in different science classes as well. So be aware of that. But those 4 shapes are kind of like the different shapes that you'll be seeing in this chapter when you graph exponential functions. Okay, so let's do one like you're going to be asked to do on your homework and on your quiz on Thursday. These are going to be no calculator problems. So can you graph 2 to the x plus 2 plus 1 without a calculator?
Yeah.
Yes. Okay, now I'm going to teach you how I would do it to make it easiest as possible for my calculations, because I'm going no calculator, right? Okay. Too much calculation right here can kind of get me when I'm keeping track of negative exponents. I'm going to have fractions, and it seems like a lot of work to me. So rather than make a table for x and f of x, I shortened this equation to like the bare bones. I'm going to call it its parent graph. The base is 2, and I'm raising it to the x. So this is like the parent graph. Making some interesting points for the paragraph should take about 5 to 10 seconds. I use -1, 0, and 1. It's going to flip my base to be 1/2. Anything to the 0 is 1, and 2 to the first is 2. If that was a base of 4, I would do 4 to the x right there, and I would have 1/4, 0, 4. If that was a 1/3, I would do 1/3 to the x, and I would have 3, 1, and 1/3.
I thought you were just supposed to make the exponent equal those values.
Okay, you could, but that's a lot of calculation without a calculator, right? And I don't want you to be like bogged down by fractions. Okay, so I'm teaching you how I would do it. This is the parent graph. It's super easy. Did you see how fast that took? I didn't have to do any calculations hardly at all.
Those are two different things.
Yes. What do you suppose the +2 and the +1 do to your graph?
Up 1 and then left 2.
Those are transformations. Those are like your h and your k's. If it's up in the exponent with x, it's an h, so it moves it right or left. And if it's being added on in the back, it's a k value. So these we can do with transformations. Okay, this graph is moving left 2 and up 1. This is x minus h, and this is a plus k. So we're relying on our knowledge from our transformations back in chapter 1. So to me, it's going to be way easier if I just plot those 3 simple points. -1, 1/2. I'm going to do that in black. So left 1, up 1/2, 0, 1, 1, 2. Those are the 3 original points on the parent graph. But Logan's right. They don't match the actual function that I gave you. So I'm going to move them left 2, up 1. And I'll always on quizzes and tests have grids for you so you'll actually be able to count out the nice points. Left 2, up 1. Left 2, up 1. Left 2, up 1. Okay, so I'm just shifting those points. What else that's really important for your graph is going to shift left 2 and up 1? The asymptote. Now think about a horizontal asymptote. Are you going to notice if I shift it left 2? No, because it's horizontal line. But are you going to notice when I move it up 1? Yeah. So I would maybe make a note to myself, move HA2 with my up 1. So now I know these 3 points are my shifted graph. I'm going to come down and get really close to my horizontal asymptote. Pretend I didn't just draw over it. I did that too. Went a little crazy right there. And then take off away from my asymptote. And this one had a base of 2, so that would be exponential growth. So that would make sense that my graph was sort of taking off. Okay, now I know there's 2 steps to that. You got to graph the parent graph, and then you got to shift it. But to me, that's way easier than trying to play around with -1, 0, and 1 in here. And then think about this. You might not get all the interesting points. Like, you don't get this part of the graph where it sort of turns. It's not really turning, where it takes off. Okay, you would just get this part of the graph where it's like going straight up. You wouldn't know where the graph is changing. So let's now fill in some of the extra stuff. What's the domain of an exponential function?
-infinity to infinity.
Yeah, there's nothing that you can't do with exponents. There's no rules. You can't raise something to the 3rd power or anything like that. Okay, so -infinity to +infinity. What about your range?
1 to infinity.
Okay, yeah. There's no graph below the asymptote. The graph starts right above the asymptote, so what will we use for our 1?
Parentheses.
Parentheses, don't include it. we talked about that, right? We're going to get really, really close to 1, but we're never really going to be 1. Horizontal asymptote is y equals 1. That'll always be whatever your k value is. If you don't have an up or down, then it's y equals 0. Okay, how can you always get a y-intercept in any math class in any chapter? Plug 0 in for x. So if I put, now I have to do one calculation, but it's pretty easy. 0 plus 2 is 2, 2 squared is 4, 4 plus 1 is 5. And I usually go check, oh yeah, I did pretty good that time. Okay, so my y-intercept is on there. Is this graph increasing or decreasing? This is increasing. And does it ever decrease? No. So we would say negative infinity to infinity. Okay. And for decreasing, I'll just do null set. Never happens. Okay. Questions, concerns? Yes, Tate.
Where did you get the red line on your graph?
Oh, so normally, remember back here when I did these two basic graphs? Sorry. The horizontal asymptote is normally at the x-axis, like for a parent graph, because it's that whole idea of you're going to get 1 over something and it's going to be really close to 0. But we talked about up here that when would you see a horizontal line move? It's going to get shifted left too, but you won't notice that. But it is also going to get shifted up 1. So it's going from the x-axis, y equals 0, to y equals 1. Yeah. Anything else? Okay, can you get out your graphing calculators real fast? Let's get out our graphing calculators. This chapter, your tests and quizzes are going to be split calculator, no calculator. So yes, you'll get to use your calculator, but some things you'll have to do no calculator, like this example. Okay. The ones that you'll be able to use your calculator, so think about that and borrow a calculator from me if you don't have your graphing calculator today. The ones that you'll need your graphing calculator today is if it has the base e. So do you remember it's called the natural base?
Mm-hmm.
Okay.
Isn't that the same thing as ln?
No,
opposite?
well, natural, that's a log with a base e. So e is approximately 2.718. You should know that from Algebra 2. I tried to describe e in Algebra 2 just like this. You know, between your 15th and 16th birthday, you grow all the time. You don't, grow 2 inches the morning you turn 16, right? That would be weird. So natural base represents what happens in nature when you're constantly growing. You don't grow on a schedule. You grow. Okay? So let's do f of x equals e to the x. I want you to go into your graphing calculators, hit your y equals menu right underneath your graphing screen. And we're going to type in the function into y equals menu, e to the x. So to get e in the calculator, you do second natural log, which is down by your 7 and your 4. And then it should bring up like a caret, and you're going to put in, or the exponent, and you're going to put in the x, which is right next to your alpha button. Okay, help each other out at your pods. Make sure you've got y equals e to the x in your y equals menu. Now, if you want to, you can do zoom 6 to get to the standard window. If you can see the graph. Doesn't look like our regular J-shaped curve. Okay. But I want to talk really quickly about how to see the table. So if you hit second graph, you should get a beautiful XY table for y equals e to the x. Do you see it? Second graph. And if you have the Casio, you go back to your main menu and choose table. Okay. Anybody not finding the beautiful table in second graph?
No.
Okay, so can you see how, in the table, you can identify where your asymptote is if you kind of scroll around in the table? If you go up towards the negatives, it just gets really close to 0. So you can kind of look and just decide, which values do you want to pick. On this one, probably -1, 0, and 1 would work. But you just kind of look for where it starts to change a lot, really fast. what is it? 0.5, or sorry, 0.4, 1, and 2.7. Will somebody tell me what it is at 2, 7 point?
3, 8, and 1.
Okay, 3, 8, so I'm going to say 7.4. And then, like, if you have that table, you can just plot those points. You pick as many points as you want. Okay, so I'm going to plot those real fast. 2.7, 7.4. And so we know the horizontal asymptote is at y equals 0. Did you find your table? And you have to hit go back to the main menu. And then you have to hit, is there a table option? Yes, choose that one. And then, yeah, choose table. I would have hit F5 right there because it said table. Okay, I'm not going to do everything else, but you can see how you could use that table function to be really helpful. Okay, last thing that we want to put in our notebooks is compound interest.
Yay.
And these will be with calculators.
Yay.
Did you get it towards Karen? Got it? Yes. Okay, these are your two formulas. I'm going to go pretty quick because we're running short on time. Yes, PERT is used whenever your problem says compounded continuously. Because it has the E, it's like what happens in nature. You grow all of the time. You don't run on a schedule. It's just constantly growing. So the only time you should use PERT is if you see the words compounded continuously. If you're using this other form, then you should be able to say what N is, which is the number of times it's compounded per year.
What? Per year, always? I thought it
Like,
was.
no, yeah, it's per year, and then the words are different. So if I say compounded quarterly, how many times do you compound per year? 4. If I said monthly, you would use N equals 12. If I said daily, we could do 365. So there'll be like some word like compounded
Annually.
blank. Yeah, compounded annually would be N equals 1. What if you read a problem and it never said the word compound? When do you think, how often do you think it would be compounded if I never specified? Once a year. Okay, if it never says compounded X amount of times, whether that be quarterly, monthly, continuously, then you'll just assume it's a simple interest, which would be compounded annually, once a year. P is the amount you invest, or the starting amount. R is your interest rate, should be written as a decimal, not a percent. And T is time in years. So if you're given months, you need to change it to years. I'll have an example for our warm-up tomorrow that is compound interest. There are homework problems, so if you need help, you can look at the examples in the textbook, or I'll post my answers or my example worked out, so you can check on my website. But it's really just like plug into the formula and work it out. So once you figure out what everything is, it's not too bad. Okay, so that's kind of like a hodgepodge of all exponentials. And tomorrow we do logs.
Ew, I hated that.
Well, it'll be the second time around, so it won't be as bad. That's what I think.
Logs are the worst thing ever.
I like